As Ellie mentioned, we had several launch attempts before we finally got off the pad. We were so desperate that last day, we decided to go ahead and turn our hats around backwards, our rally caps. It must have worked because we managed to launch.
Here we are on the launch pad with the final few seconds, and feeling like we're finally going to go. We heard the main engine start at about 6 seconds prior to the launch. We could feel the twang, as they call it, and then at booster ignition, off we went. And I'll tell you, it was quite a ride. I guess from the ground it looked pretty spectacular because the shuttle was hidden by the smoke and vapor right after liftoff. As I mentioned before, we were all pretty happy on Ascend, having an opportunity to look out the window, feeling comfortable. And one name I didn't mention that I really ought to is Joy Barcolt. She was the team lead of all the trainers, and she really pulled us and them together, I think. We were going uphill pretty quickly. At this point, you'll start to see some vapors as the shock waves build up on the nose of the orbiter and external tank as we pass through the region of maximum dynamic pressure here. The shuttle really vibrates a lot. It's, you know, it's the ride of your life. It's about all I can say. This is a nice view of us as we punch through a cloud deck there, and the shadow gets cast on the top of the clouds. SRB separation was just like it is in the simulator, I thought, a bright flash, a little pop, and all of a sudden the ride changes from being really abrupt and vibration to very smooth.
First thing we do on orbit is open the doors and deploy the KU band. That was my job and Mike's job. And that, of course, is the source of all the TV. And on this particular mission, we had digital data, 6 channels of digital TV down for the experiments, which was really just great in terms of data management and resource management for us on board and the folks on the ground. But the first job that, right after opening the doors, what Mike and Fred and I had to do as the blue shift or the night shift was go to bed. This is probably the hardest thing that we had to do the whole mission because it was just, I just can't tell you how exciting Ascent was. As Mike said, it's the ride of your life, and it's something I just still look back on and just grin. And going to bed, well, I'll just say, at least we shut the doors.
In addition to wearing our caps backward, I wore my lucky socks on the day that we finally got launched. That was the key to it. 2 St. Christopher medals didn't get us off on the second attempt, but the socks did it. After 30 days of quarantine, I knew I was ready to launch, but I wasn't sure I could remember what the mission was. But when it came time to do Space Lab activation, it was just like in the simulator, only nothing broke, and everything powered up just like it was supposed to. We didn't power off the lab, and we didn't do any hot coupler swaps, so we stayed in good graces there. Everything came up just like it was supposed to. We were amazed and delighted. We had a fairly light day scheduled on the first day to accommodate anybody who might not feel well or Space Lab systems that might not feel well. And we didn't have any of those problems. So what we ended up doing on our first day is really set the laboratory up well for a 2-week space station. Make it useful to do all the experiments we needed to do over that time.
While Kathy and I were setting up the lab, Kent and I were doing a trim burn to get us just in the right orbit. We rolled the payload bay door partially in on the port side and went into the gravity gradient attitude. Then the next 15 days were pretty much the same, and they usually started like this.
Much like here on Earth, you brush your teeth. What I wasn't prepared for was after I was done brushing my teeth, there's no sink up there to spit this stuff out in. And so, yeah, I had to have an alternate plan. And mine was to kind of swallow it, and it didn't work out that well. You saw Al Shaven, which is very much like here on Earth, and Mike now is riding the ergometer. And that was our main means of exercise. And we exercised every day on orbit. Along with exercise, though, comes the overhead of cleaning up. And without a shower, the sponge baths take a while. And then also wash on our hair. We had a rinseless shampoo that worked really well, and Katie's demonstrating it for us here. And you'll see in a minute, she managed to get her hair dry.
I figure if I keep my hair clean, everybody can. It worked out just great, actually. I was a little worried about it before flight, but keeping clean up there was no problem. Now this is, I'm at the glove box doing that protein crystal growth there, and I'm actually using a restraint system developed here at JSC called Albert. We refer to this as Albert the Thing, as opposed to Albert the payload specialist. I'm working on protein crystal growth, and as you know, these crystals are used to help design drugs for diseases, and it's kind of a lock and key sort of effect where if we can grow more perfect crystals, we know what the lock looks like, and the drug is then the key.
Here I am at the glove box again on Albert, so to speak, or Al squared. And we're working in the glove box, and I'm really looking at mixing profiles. It's very important in the zeolite community. Some of the zeolite community don't recognize that, but it is when you bring two reacting liquids together. And on orbit, we have some special problems. This is the bubble generation here. We talk about bubbles, so sometimes we don't want those bubbles. And so now that we have them, what do we do? And what we do with them, and this is the main experiment that I use that information to power up and to generate, is you'll see me rotate this cylinder which has the solutions in them after we mix them. And we rotate it in order to take advantage of centrifugal force and throw the heavier fluids to the outside, the bubbles to the inside, so they make one big bubble, which doesn't have what we call a lot of nucleation sites, and allow us to grow fewer but larger crystals with fewer defects. So that's one of the things that we had learned on USML-1 and confirmed again on SpaceHab. This is called CGF. We're doing electronic crystal growth here, and Kathy's in the glove box, a closed area. Very difficult task to take in and out what we call SACAs, and I help her a little bit once in a while, and the commander's documenting it, so if we make a mistake, everybody knows we made a mistake. But we didn't make any mistakes that we'll admit to. And here I am taking the SACA very carefully down to stow, because as all PIs, including myself, they're a little bit paranoid about shaking and vibrating, so it'd be a terrible thing for one of the PIs to ruin a crystal, so I made sure we didn't do that.
In this shot, I'm interacting with the geophysical fluid flow cell experiment. This experiment, again, simulates convection in planetary atmospheres. In this view, you can think of it as a weather satellite, basically looking at the southern hemisphere of the planet. The pole is at the bottom of the screen, and the equator is at the top, and you can see waves propagating around the equator, and somewhat reminiscent of cold fronts propagating down from the pole. Another fluid experiment was the surface tension-driven convection experiment. We all spent a lot of time on that one as well. Basically, in that experiment, you can heat the top surface of the liquid, and because there's a variation in surface tension with temperature, a fluid flow occurs at the surface and also drags around the interior of the fluid. And this experiment has a lot of importance not only to the film coating industry, but also has impact on crystal growth. In this fluid experiment, we were looking at manipulating a drop using acoustic fields. This experiment also had applications to drug delivery systems, and there's a lot of interest in surfactants. In this particular case, we're rotating a drop until it fissions.
This was one of the experiments that we all fought to do. Get up in the morning, you were always tempted to actually change the payload activity plan so that you'd be the one doing drop physics. Because as you can see, each input that you make to this acoustic chamber actually changes very dramatically what the drop does. And so we have a chamber with speakers on all sides, and we're changing literally the speaker pressure to distort the drop and also to do to maybe spin it around like this. What you're going to see coming up is, in just a minute, is one particularly interesting experiment that we did where we actually brought two fluids together. This isn't quite it yet, but we used this experiment to learn what happens when we do have two fluids, what happens when we have a bubble inside a bubble. But when we brought these two fluids together, they actually had an interface in between them, which we refer to as the beach ball. And what this is going to be used for, it was a development model for actually forming vesicles for drug delivery systems. Now, we didn't really develop a drug delivery system, but we did look at the way two fluids would interact in a single chamber. You can see that's what happens when you do the wrong thing with the knob.
We had, as Katie said, 6 channels of video down, and this may be the first space flight or space lab flight ever where video downlink was not the limiting resource in planning. And also, most of the PIs left Marshall at the end of the mission with all of their data, whereas on USML-1 it took 7.5 months to get all their data out to them. So this was the first demonstration of that. It's something that we'll certainly need for space station. And that and the data uplink and downlink we had were kind of the first demonstrations of telescience that I think we've ever done. Another fluids experiment we had on board, which was an awful lot of fun, was the fiber-supported droplet combustion experiment. We put a small drop of a fuel on a fiber, and the only purpose of the fiber was to keep the drop where we wanted it to be, and ignite it. in one camera view, this one, you could just see the drop shrinking as it's being consumed. In another camera view, you can't see much of the color of the flame front, but you can see that the fiber on either side of the drop is being heated, and that's where the flame front is propagating. We learned a lot from doing a drop physics module on how to deploy these drops and get these guys burning. There was a little bit of trouble with this experiment, as anybody who worked the flight here knows. Mike was our IFM person on this and got it working.
We also had another series of theoretical, I'd call them, experiments on crystal growth, and what we were looking at is hard sphere models and how they would represent the formation of a crystal structure and the interface between that crystal structure and the fluid from which it formed. And we also use lasers to look at diffraction patterns to find out exactly where that interface was and what kind of crystal formed. And the crystal structures that were formed were not those that were predicted. They're still analyzing why that is. So that was kind of a surprise.
While the payload crew, the four of them were in the lab, the orbiter crew, we had some experiments up in the middeck too that we were working on. We activated and deactivated some protein crystal growth experiments. We also, I'm from potato country in Colorado, was pretty proud of the fact we managed to grow 5 potatoes in space. And I'll let Mike talk about that.
This is just an example of me giving some CO2 to the plants inside, and the real goal behind the experiment was to determine how to make a nutrient delivery system, both water and other nutrients, to the plants in case we, for long duration missions, we need to know how to grow those foods so that we don't have to take them with us.
We also did our part for medical science, and here I'm doing a neurovestibular DSO, and it has to do with the rate your eyeball contract.
Well, this is how we got all those Earth Ops pictures you saw at the beginning of the presentation. Take one of those big Hasselblad cameras, point it out the window, and this is the scene that the operator would see. Up in the top is the west coast of California. And you can see the greens of the trees and the mountains, and then the yellow stripe there in the middle is the northern San Joaquin Valley. Next green stripe is the Sierra Nevada, and then you'll see the browns of the high desert. Lake Tahoe and Pyramid Lake will just start to come into view. You can see it doesn't go by very fast. Most of you have seen this sort of view before. But you really realize you're going fast when you think of the distance involved in just this 30 or 40 second picture. First week we had really clear views of almost the whole United States. So we got to take a lot of shots of a lot of different cities, especially potato country in Colorado.
This next sequence here is over we're currently over India now, looking north, and those are the Himalayas there in the middle of the screen, with the Brahmaputra River both on the south side of the Himalayas and also on the north side of the Himalayas. And you can see the vast difference in both color, which basically is vegetation, and also elevation. This was Super Typhoon Angela, which was taken over the Philippine Sea, which hit that set of islands with winds over 200 miles an hour. And you can just make out the circular formation in the clouds, although on this particular shot you don't really get any sense of an eye in the middle of the hurricane, but it was certainly strong nonetheless. This was an attempt at a night scene. We were over sort of central United States here looking west, and with that line on the left isn't the horizon, believe it or not. It's the edge of the atmosphere, and that'll become more clear in a second. But if you watch this star up here, it'll actually go below it, and you'll see it what it will look like through the Earth. So that's clearly not the edge of the Earth. So this is the thickness of the atmosphere. And these are the lights of big cities. There were Washington, Baltimore, Philadelphia, and here comes the Big Apple. And as the sun rises, which is about to do, it washes out the camera. The sensitivity changes, and sort of made our own fade to white, I guess.
The daily maintenance was done, and filter cleaning, and being a pilot, I got to do that. And filter cleaning I enjoyed a lot more than keeping the WCS clean. But unlike here on Earth, dust, there's no floor, there's no dam, so dust accumulates in the different places in the filters because it's always floating in the air. So anywhere it's drawn, you've got to make sure you get to it Space did lend itself to some innovative cleaning styles that were a lot more fun up there than on Earth.
We carried another computer on board to do the pilot simulation. That was a really useful piece of gear, I thought, to help me prepare for my first space shuttle landing. And this is what it looked like on the scene, just like out the window of the real orbiter.
This is the Blue Crew enjoying lunch. As you can see, I'm finishing up my lunch back there. Fred is cleaning his silverware with a handy wipe, and Katie is probably reading the news, some humorous story. But we did that. We got an hour off in the middle of our 12-hour day, and the mail we'd get up electronically on a keyboard, sort of like email.
We got our mail up on the KCA link. I'll talk about that after the World Series, maybe.
Yeah, you may have seen us. We got the chance to throw out the first pitch in Game 5 of the World Series, which was really a lot of fun. And more importantly, we got a chance to watch it. You can see us in the lower right-hand corner watching the monitor, and we're seeing the image that you see in the upper left-hand corner.
And at the end of the mission, or close to the end of the mission, we had put everything away. We were getting a little bored, so we decided that we'd do a little magic show. And I've tried for years to do that, never been able to do it. But now the trick was to get her down without doing something bad.
What I was telling you.
Al was a pretty good magician. It's important to take those breaks on orbit. They help you stay recharged and do good work while you're up there. All good things have to come to an end, and this is how we started getting ready to come home, checking out the systems on the orbiter. Then it was time to close up the payload bay doors, say goodbye to the view out the window, and get ready to come home.
The entry was spectacular. Being a first-timer sitting up in the front, the orange-pink glow was just fantastic looking through the windows. This was a shot on entry taken from a guy in Denver on top of his house with his handycam and sent it to us. Anyway, we came around the hack shortly after sunrise, coming down the 18-degree glide slope at 300 knots. SOX just had the guidance nailed, doing a beautiful job. And it's very dynamic. It's like trying to land a bomb, because this is similar to a bombing profile that you'd fly in the Navy. I got the gear out at 300 feet. We came across the threshold right where we should have been, touchdown 2,500 feet down the runway. And the landing was so smooth, I'd like to take this chance to brag about SOX. And it's uncharacteristic of a Navy pilot, but this landing was so smooth. It was like on an airline landing, when the landing is so smooth, everybody in the cabin just claps and cheers. And in fact, that's what happened on our landing when we touched down. You could barely tell we'd touched down.
Ken had to do the most important thing on the mission, though, get the gear down, and you can see he did that successfully. Columbia was a beautiful vehicle. It was a little slow getting off the pad, but it was worth the wait, because when we got up there, there were very few problems. And it really proved itself to be a wonderful platform for science.